Nope, preached on my way out, Motra. Hi, everyone. Everybody here? I think, maybe. Let me make sure nobody's left in the waiting room. We're recording? Yes, we're recording. Okay, good. How is everyone doing today now that we're all stuck in the same place and can't leave our house for anything? Sheltered in place. Those of you not in Fresno, hopefully you're allowed to leave your house. We'll wait a couple more minutes to see. Oh, there's one more person in the waiting room. Hold on. Let everybody in. And I'll mute you guys. Sounds like someone has a little one like I do. Somebody asked what chapter we're on. This is going to be continued of chapter 17 and 18. So this is still viruses today. I'm mainly going to go through just the two viruses. We're not going to have too much stuff today. I'm going to give you guys a couple of alternate assignments as well. So we'll talk about that. I'm going to give one more minute to see if anybody jumps on. We have about 17, so give it another minute or so. Participant list is there. Everyone noticed that I'm in my son's room today, who is very fond of planets. So we've got the solar system above me here and some rocket ships and such in the back. My 2-year-old is running around, so I'm locking him out by being in my 5-year-old's room. Don't worry, my husband's out there too, so he's not by himself. Okay, let's see if anybody else has jumped into the waiting room. All right, well, if I see anybody else jump on, I will also stop. And there's a function on here called the waiting room. It lets you to see who has jumped on before starting the session. So when you first log on, you might see that you're stuck in the waiting room. I just have to admit you into the official Zoom meeting once you guys get in there. So sheltered in place, everyone. All right, we're stuck here a little bit more. So lab, as I sent yesterday, we are not allowed to go on campus at all. I got an email from the provost this morning saying that we are going to limit any sort of non-essential tasks on campus, meaning that not anybody who's not currently living on campus or part of campus safety or some essential function of campus. They're just going to limit whoever goes on campus. And I have books trapped in my office, so I'm going to actually attempt to get into my office later today just so I rescue my books, because I did not know that that was going to happen and I wouldn't be able to get into my office. But anyway, so we are not allowed on campus. Anybody who is participating right now in a 496 project, I specifically asked about 496, which is the independent research. Right now, they are going to say hold off anything until April 1st, but that you guys will be given the priority to do research on campus if that is available. So if you guys are participating in that, right, just hold tight until April 1st. And hopefully we'll know a little bit more about that. And then they still haven't made an official announcement that we're going online for the rest of the semester, but I think we probably should plan that that's going to be the case for the remainder of the semester. Again, if any of you guys have questions about that, please email me. I can talk with you about it. Oops, I gotta let somebody in. Okay. All right, so today I'm just going to talk a little bit about COVID-19. We're going to go through a couple things I wasn't able to go through on Tuesday, and then talk about influenza, and then I'm going to introduce you to the two online assignments that I'm going to have. One will be due, if you can, by Sunday, and then the other one will be due a week from Sunday, so you'll have a little bit more time to complete that. Both of them are pretty short assignments. We shouldn't take you more than probably at most an hour each, probably much less time than that. So let's get through some of more COVID-19 fun. I'm trying to move you guys' faces out of the way. How do I get you out? How do I move you? I need two screens here. All right, another thing I'm gonna steal from my office, another screen. Okay. Oh, that's better. Let me move you this way. All right. So the first slide here, can everybody see my slides? Thumbs up, yes, hopefully. I'm gonna unmute you. Yes, everybody can see my slides?
Yes.
Yep.
Okay,
Yeah.
awesome. I'm gonna mute you again, sorry. Ooh. Okay, so this, the first slide here, let me get my little drawing apparatus. Well, I'll just use my pointer maybe. This drawer is not the easiest thing to look at. So this is an electron micrograph of the COVID-19 or the SARS-CoV-2 virus. And you can see kind of in that middle portion there, the envelope, and then the red portion kind of where the RNA is located, and then those little spikes up here. Right next to that is this artist rendition of it. And one of the things that we didn't get to talk about last time is the attachment. So we talked a little bit about attachment of viruses in general, but we didn't really talk about attachment of this particular virus. And that's one of the things they first started looking at when this virus started coming into the population, is looking for what the receptor was and what portion of the virus itself attached to that receptor. And then it's a little kind of hard to see. I did upload a version of this on Moodle so you guys can take a look at it. So this portion, that kind of like teal, orangish, reddish portion right here, is the spike protein, the S protein on the outside of the virus. And it's supposed to be attaching to a receptor here, and the receptor is called ACE2. It is a receptor that's located on a special type of cells in the lung, alveolar cells. Hopefully most of you have taken physiology or kind of remember from Gen Bio the structure of the lung and kind of what the lungs are doing, right? So we breathe in air, the oxygen comes into our lungs, and within the very tips of our lungs, the alveoli sacs, is where we have exchange of oxygen into the bloodstream and then CO2 back out, so we can respire back out the CO2, right? So these alveolar cells are cells that are located in that area of your lung. So they're very, very important for exchange of oxygen. So this virus attaches to a receptor on those, some of those specific cells within that portion of your lung. This is very similar to SARS, the SARS-CoV, the original SARS virus that we talked about last time. It uses that same receptor to attack cells. So this tissue type, the specific tissue type that this virus is attacking are these alveolar cells within your lung. So they're not cells in your nasal cavity. They are cells in that very important portion of your lung where that oxygen exchange is happening. So a very bad place to have a virus and to have a virus attack those cells. One of the papers that came out recently, does this have the date on it? It was fairly recent, within the last 2 months or so. This is just a nice picture from that paper, although probably the artist rendition could be a little bit better. But it's comparing the SARS-CoV, the one that causes the SARS disease we saw before, and our new friend, SARS-CoV-2. And it even has a little bit of, and you can tell this was very old because it has the death rate in the cases so much lower than it is currently. Had it at 50,000, so this was a while back. But they both use that same receptor. So that's supposed to be the ACE2 receptor, again, on the alveoli cells to gain entry. And this specific paper was looking at a potential treatment that helped to block that. Again, it's not something that we're currently using as a treatment, but it was like, hey, this is a potential target of maybe something we can use as a therapeutic to block this virus. We will talk about a current clinical trial for a treatment that is happening in Japan at the end of this section this morning. Okay, so the receptor that SARS-CoV-2 is using is called ACE2. It is located on alveolar cells, specifically type 2 alveolar cells. And that's what it's using as that attachment point so that it can get into the cell. Okay. So a lot of terms have probably been thrown out if you have watched the news at all or heard any news about this virus. And you may have heard that term incubation period. And I was planning in chapter 22, I think it is, talks about the infection and kind of the route of infection, but I thought I'd bring that to you a little bit earlier since it's kind of important when we're talking about this virus about what the heck is incubation period. Well, this is kind of a generalized graph of a disease, and a disease specifically caused by microbes. So that period right here in the beginning, little annotator thing. That little period between, this is supposed to, right here at the beginning is like, the virus, you get coughed on, you introduce it into your nasal cavity. So the second that virus comes into your body, right? And then it goes through a time between 0 viruses in your body where it starts dividing or replicating, right? It starts infecting cells, it starts replicating. So there's a window of time between when you get the virus into your system into when you start actually showing some sort of symptom, right? So usually that time from the period you get the virus introduced, or if it's a bacterial infection, same thing, the bacterial introduced into your body, before you actually start showing signs of an illness, so the period of illness. And we call that period of time the incubation period. So the incubation period right now for SARS-CoV-2, we don't know. We think it's somewhere between 2 and 14 days, somewhere in that period of time. And but we haven't done enough studies on it to see exactly what that incubation period of time. That becomes really important when we're looking at testing. And when is the test most accurate? If we test anywhere in that incubation period, are we going to have enough virus in our system that the test will come back positive? Or is it going to come back negative as a false negative when we do actually have virus in our system, but it's not enough that the test is reading it? So that incubation period, again, is the time between when the virus is first introduced into our body and when we start showing symptoms. And let's talk about symptoms again. Okay, so this virus, what are those symptoms? Get back to my mouse. This is a graph similar to, well, it has kind of the similar symptoms that I showed you guys last time. This one, there's a website called Our World in Data. It's actually a really great website for a lot of different statistics. I mean, anything. There was something about like the carbon footprint of eating different meats on there. I mean, there's a lot of stuff on there. But it does have a lot of good information about COVID-19 and current disease. So this is specifically looking at cases in China. So I think, yeah, February 22nd. So this was even a while back, but it seems to be pretty consistent. As more data gets reported, we'll see if that changes at all, but this is from the cases in China. So the number one there on top at almost 88% is fever. So that's the number one symptom is fever. Then following that is the dry cough, fatigue. So just kind of feeling like crap. Sputum production. So being able to spit up something, mucus, etc. Shortness of breath, muscle pain, sore throat, headache, chills, nausea or vomiting, nasal congestion, and the diarrhea are way down on the bottom of the list. So most consistent symptom is fever. Okay, so how are people actually dying from this virus? What is causing death in the cases that people are dying from this virus? So the virus is getting into your lung tissue. It's invading the cells that are important for exchange of oxygen. So the death will occur by respiratory failure, basically complete systematic failure of your lungs. We call this acute respiratory disease syndrome. It is the same disease cause that SARS, the severe acute respiratory syndrome, the other virus, also causes as well. So I pulled this from a paper specifically, and I know it's got a lot of detail. It's got a lot of information on there. I just wanted to show it as kind of a good, like overall of what is happening in that portion of your lungs that is leading to ultimately death of these patients. So on the left-hand side here, we've got the normal alveolus. So this again is at the very tip of your lungs. This is where oxygen exchange is happening. So you can imagine here, oxygen is leaving, coming into your blood system, CO2 is coming back out, so you can respire that CO2 right back out of the system. So this is a really important portion of the lung for that gas exchange to occur. We don't have oxygen, not so good for our body. So the type 2 cell right there, that's the cell that this virus is invading. And basically, if you look on this side, during that acute phase where these are so damaged, we've got this super, for those of you taking immunology, influx of immune cells right here. So we've got a neutrophil and a macrophage. We've got all these immune cells coming in here, basically just huge inflammation, right? Basically, this whole area is getting inflamed, it's full of fluid, and it can't effectively do its job. So if at the end of all of your lung tissue in the alveoli of all of the lung, completely inflamed, they can't do their job of exchanging gases, it's going to ultimately lead to death. Wow, what a pick-me-up this morning. All right, okay. Let's move to the next one. Okay, but this is not happening in everyone. So this lovely pyramid is representing, again, these are cases, I believe they are in China. Yeah, these are all in China, and this was again up until February, but again, pretty consistent to what we're seeing. So most of the cases, 81% in this case, are mild. You generally feel bad, cough, maybe a little bit of fever, maybe not. Very, very mild. 14% are what we consider severe cases. So they probably need hospitalization. they're having some sort of trouble breathing, can't get enough oxygen in, have to be some supported respiratorily to get enough oxygen in. And then 5% being those super critical cases, where it can lead to septic shock, so complete blood infection. And then about 2.3% of those cases are actually leading in death. So the majority of the virus is not, or people that are infected with this virus are not having that very severe where they need to be in the hospital, but enough that we need to worry about it happening. So 2.3%, this number is not exactly set in stone right now. We don't have the case fatality rate at this point, and we probably won't know for a very long time. What is happening with testing, especially in, well, not here in the US so much yet, hopefully we'll get there, but in the other countries, is that when a case does come into the hospital and they can confirm that there is a case and it's somebody severe enough that they've had to make, they've made the trip to the hospital, they do what epidemiologists call kind of they go out and they find everybody they had contact with. So that person, they confirm that they have the illness, they'll go around to all their friends, family, who they contacted, and then start testing all of those people. So that's where the numbers of cases start going up and up and up, even though maybe the majority of them didn't have enough symptoms for them to even report into a hospital to notice. So that's the only reason that we found them, is that they're doing their due diligence, come in with a case, then they start testing everybody that case came in contact with. So as we get to that point for more and more people, the case number is going to go way, way, way up, and that will bring the death rate down. So the more people that we have that have it, the number of percentage that die go down very, very little. So as more and more testing happens, we'll start seeing that death rate probably going down a little bit to who knows how low it's going to get when this is all said and done. So who is the most affected by this? Probably many of you have heard this, that it's mostly older people. But all of this data, or most of this data, is from China. And there was a report just released today, I think it was this morning, that there is more younger people here in the US being hospitalized than we saw in China. We don't know why. They did not have any additional information about if any of those most of those people had an underlying condition. But it seems that 29% of the people here in the US are younger people. So 20, 30-year-old range that have been hospitalized, not that have died, but that have been hospitalized. So this is what we knew before that. We got to have more data. Okay, so let me get my little draw here. So those who are age 60, this is what we originally thought, and this was true in China, are the ones that are most at risk. So if we look at, this is infected, so percentage of people who were infected that actually died. And up down here on the bottom, you can see this is 80% plus, that we're really looking that percentage is much, much higher than that overall 2% that we saw on the last slide for if you're older than 80. And then here on the left side, we know that if you have an underlying condition, so cardiovascular disease, diabetes, a chronic respiratory disease, one of those like COPD, high blood pressure, and then cancer, your chances of dying from this disease are way, way up, where if there was no pre-existing condition, the percentage was down below 1%. So older people with a pre-existing condition were the #1 targets for severe, almost always leading to death, or having a greater percentage leading to death. Again, a report in US just found out, not necessarily true here in the US, so stay tuned to that to see what's happening. Another very notable thing about this virus is why no kids? We have no idea. We have really no idea why kids are not being affected. This is still true in the US. The numbers that came out was a very, very small population of under 19 or being infected or being effective enough to show severe symptoms so that they've been tested. So we're thinking maybe the virus is in a lot of under 19s, but they're not showing any sort of symptoms, or they're so very mild. I mean, my 2-year-old has a runny nose like pretty much his entire life. So if he had a runny nose, we wouldn't think anything different. So maybe that's it. There's also a theory out there that maybe because kids do get sick so often, that they might have a little bit more immunity to corona-like viruses. We don't know. One of the reasons that we think, because as I mentioned, coronaviruses do cause common colds. One of the reasons that we think that we get reinfected with coronaviruses is not necessarily that they're mutating so fast, but that our immune system is actually forgetting fairly quickly that we've seen that coronavirus, so we're able to be reinfected, where with other viruses or other bacteria, we wouldn't be able to be reinfected. So we're not really sure exactly why kids are not getting the same infection that we are. Okay. We haven't talked too much about this idea, but this is I like this slide. It's from a book I used probably like 4 or 5 years ago, that shows how we spread infectious disease from one person to the next. And it just gives you an overall summary of kind of the ways, how do viruses spread? How do we share our viruses with our friends and neighbors? So there's a couple of different ways that this specific virus is getting transferred from one person to the next, so that we kind of group these into 2 categories. Direct, from me as a person, are gonna give it directly to you. There's not gonna be any sort of intermediate. I'm gonna share it, I'm gonna give it to you. And then there's indirect, where I'm gonna put it on something else and you're gonna touch that something else and then bring it into your body. And we call that indirect. So you can use your imagination, the pictures kind of help you there, of how direct contact works. So direct contact, I make out with you, I'm gonna put some direct contact between me and you. So kissing, any sort of touching where our body parts are actually touching each other, that's gonna be a direct contact. So in the case of this virus, if my husband and I decided to kiss and I had it, I would give it to him. So that we could share the virus directly with each other. Same thing if with droplets, as my 2-year-old likes to do quite often, if he spit or sneezed or coughed in my face, that would also directly transmit it to myself. Mother and child in utero, and then biological vectors, and this is not something the COVID-19, but with things like West Nile or other malaria, things like that, a direct vector like a mosquito biting me and then going on to the next person. Indirect is when I cough or touch a surface, leaving it on that surface for the next person to pick up. And we'll see how long that lives on surfaces on the next slide. So I had a question. How long does it take for people to become healthy after COVID-19? We're thinking about 5 to 10 days. It just depends on the person and how severe the illness is. People without severe illness are getting better much quicker. They just feel bad for a couple of days and then they're okay. So we don't know the exact course of the infection for everybody right now. I know that they're working on that data. And as we get more and more cases kind of going through and compiling all that data, kind of exactly where symptoms are starting and finishing. But the fever for most mild cases is kind of 3 to 5 days with that really kind of severe fever. Okay, so we're really worried about this virus transmitting through a couple of different ways, person to person. And then surfaces. So one of the big things that they've been saying is everybody wash your hands, right? So it's okay if I cough on a surface, you touch it, and then you wash your hands, right? That's not going to be transferred into your face. So as long as we're stopping the transfer of the virus from that surface into one of the portals of entry on our body, we're okay. So cleaning surfaces very often with something that is actually going to kill the virus. Somebody asked if you're able to get the virus again. So there have been reports in China of people being infected twice. So they've recovered and then they've gotten the virus again. The second time it seems to be much, much more mild. So it's barely even noticeable, but they are able to be infected again. We have no idea why, because our immune system should be able to fight this fairly quickly. Again, when I was talking about that, our immune system kind of forgets about coronaviruses. We think that may be happening with this virus. We're not really sure. Okay, so surfaces. This came out on the 17th, so Tuesday. And this was a testing specifically of, I think this group is at, oh God, I can't remember where they were. You can click on the link and look and see what lab they're in. But they were testing the survival of this virus on different surfaces. And also an aerosol. So aerosol would be that I cough, and how long do the virus survive in those droplets? And you can imagine, if anybody watched that video that I posted about the spread of the virus where that guy sneezes and you see all the little droplets of stuff with the virus in it. So you can imagine if it's a larger droplet, it's going to fall down fairly quickly. But some of the smaller droplets, and viruses are so small that they can kind of live in these smaller droplets or survive in these smaller droplets for quite a period of time. And so this group was looking at how long does the virus survive in the droplets, or how long does it survive on surfaces. So you can see this, here's a couple of different surfaces they looked at. They looked at copper, which looks like it kills the virus pretty effectively, or it can't survive very well. Let's go line our whole houses with copper. All right, so copper, cardboard, which is important for all those Amazon packages everybody's getting, stainless steel, and plastic. So those were kind of the surfaces they tested. And then here's that aerosol one here on the very left-hand side. So this represents the two different viruses, the SARS-CoV, the original one, and then SARS-CoV-2, our new friend here. So I believe one is the blue and then red is the 2. So looking at survival. So this is, if you look on the y-axis here, we can see the titer. So that's how, titer just means how much of the virus was in there. What is the quantity of virus in there? And it goes anywhere from 0 to 10 to the 4th is up here on the top. And I think the scale for all of them is the same. Good job, New England Journal of Medicine, keeping them consistent. It makes it very easy to compare these. And then the dotted line represents kind of below the detectable levels for what they were testing. So we can see that aerosol, it's surviving a little bit longer. So this is how many hours. So we're still getting survival in aerosol with those little droplets for a couple of hours after a cough. Not good. We thought it was going away fairly quickly, but it seems like in those aerosols, it's surviving a little bit longer than we thought. Copper seems to go down pretty quickly, which is great. Cardboard, somewhere about 24 hours here, we get down to non-detectables. Stainless steel is about the same. Plastic, maybe a little bit longer. So we're looking somewhere between 24 and 48 hours on surfaces is kind of the survival rate right now. So somebody is concerned about, you know, packages coming from China or all the stuff that we get from China. Well, if it's going to get on a boat from China, nothing's going to survive by the time it gets here. So we need to be more worried about our neighbors that are infected. Okay, so new treatments. This came out yesterday. Yes, yesterday. So there is a Japanese drug that is currently on the market there for influenza, so the normal flu virus, and they are starting clinical trials, and it seems like it is promising against this coronavirus. So stay tuned for that. Maybe that would kind of save all of us right now. So yeah, they're in clinical trials. We'll see how that goes. Maybe there'll be something on the market. And then the good thing about this one is that it was already approved as an influenza drug. So it doesn't have to go through the same trials as it would have been as a brand new drug on the market. So hopefully that means that it will get to market faster than if we would have been starting from scratch. So stay tuned for that. All right. Does anybody have any other questions on coronavirus before we jump into influenza? All right. If I see one pop up, I can go ahead and go back. It's okay. So let's talk about an old virus. Poor guy is not getting any spotlight this year. Influenza. So influenza is also an RNA virus. Normally this time of year, influenza is the one that's getting all the attention. Our last big pandemic that really affected the US, and there was a nice graph, and I should have grabbed it from that website, the World Data, that showed that, and this was in 1918 was kind of the peak of that influenza outbreak. We call it the Spanish flu. And you can see at 1918 in most countries, the life expectancy, so how long people live in this country, had this huge drop. And it actually changed the life expectancy in most countries. I'm sorry, I was just reading a question. I'll get back to that question in a second. Let me talk about influenza first, and then we'll go back to that. Okay, so that was our last big pandemic, the one that did actually shut down schools, and we were kind of in a similar situation then, with not great consequences for many cities during that 1918 pandemic. So influenza, we know that influenza is able to infect other mammals besides us. Avian, swine are the two big ones. So you may have heard of, 2006, 6, somewhere around there, we were expecting that H1N1, which was an avian flu, may be our next flu pandemic. And we were starting to stockpile for that flu pandemic. And we put in place a lot of preparations that we're using today for this pandemic during that time when we were worried about avian flu. So it's able to cross between different species. So swine to humans, humans to swine, swine to birds, back and forth. The virus genome of influenza is very interesting because it has 8 segments of RNA. So as we talked about, coronavirus, it just had 1 segment of RNA. Influenza has 8 different ones. The outside of influenza has 2 very well-studied proteins. We call them H and N for hemagglutinin and neuraminidase. The H protein is important for entry of the virus, and then the N protein is important for release of the virus. So this is a nice artist rendition of the influenza. It has the capsid and then the RNA information in the middle. So here is those 8 segments of RNA in influenza. We've studied them, we've sequenced them, we know lots and lots about them. And you can see that H and the N protein here, encoded here, some different matrix proteins, a transcriptase, an elongation, some protease. So they all have different functions within the viral replication and release. So influenza is one of the big ones that we have a huge problem with every year because of 2 ways the virus is able to mutate very, very effectively. And we call those antigenic drift and antigenic shift. So there's 8 segments, and every single one of those 8 segments can mutate on its own. So the nucleic acid information in the RNA can change. So the sequence of that RNA can change. leading to changes in the viral protein. And we call that antigenic drift. So if we've got a sequence of like A, U, G, U, C, and that changes to a different sequence, that will lead to a change in the protein, and we call that drift, okay? And within any given species of influenza, that can happen. Changes, it changes, it changes. Changing those H and N proteins, changing the way it releases, changing the different proteins that the immune system can't recognize it. In addition to that, if we get within one host, 2 different viruses with 2 different genomes, they can start swapping pieces. So one virus can pick up one segment, mix it with another segment, and now we can get rearrangements of the segments within 2 different viruses in the same host. And we call that antigenic shifts, okay? And I got a nice little picture of what those 2 mutations call. So we got antigenic drift. Again, that's changes of sequence within the RNA, and then shift, where different viruses are swapping segments, whole segments of their RNA genome. So this goes through a couple of those ideas. So here is the 1918 Spanish flu, the Spanish influenza. And that influenza was what we call H1N1. And that went from birds into humans. Okay, so it jumped from birds to humans. And they're representing in this picture that it's got kind of like those bluish green RNA sequences. So after that, we had another strain of influenza in 1957, where we had that same H1N1, okay, and that mixed with an H2N2, where they were able to shuffle their genome. So now look, we've got a new virus that has some of the segments from H1N1, here are some of those bluish green ones, and then some of the segments from the H2N2, right? So here, there's that little guy right there, he moves there. Now in 1968, the Hong Kong influenza, we had a H3 strain of avian mixing again with this H2N2, and now we've got an even more different virus here because we've added some of these yellow segments in here. So now we've got a completely different viral genome based on that. So we're worried that that would have been our next pandemic. Well, SARS-CoV-2 kind of got in the way of that. Okay. So influenza gives us this good example of how mutations within the genome, as well as swapping genetic information, can lead to completely different viruses. So every year, we do not know what influenza strain is going to emerge. Because of this genetic drift and genetic shift, we have to guess every year which one is going to be the big one. And we, the manufacturers of the vaccine will do surveillance and say, okay, we're surveilling birds, we're surveilling pigs, we're surveilling humans. What are the strains that are out there? What are the strains that are potentially going to lead to the next huge outbreak? And they make bets on which ones they think that is, and they make the annual flu vaccine towards those different flu strains. Now, sometimes they guess right, or they get it at least fairly close, that most of the time the vaccine is fairly effective. If you get it, you should get it. Everybody should get it. It's a good thing to get. Every year, get one. Okay. Sometimes they're off a little bit, and it is not as effective, but it is usually a good bet, even if they don't get the exact right strain, that the vaccine should give you at least some protection and prevent you from getting a very severe case of influenza year after year. Now, having a different flu vaccine every year is not the best way to do it. But unfortunately right now, that is the only way. But the scientists are out there trying to create what we call a universal flu vaccine. So meaning that no matter what genetic drift and genetic shift is out there, that we could have the same vaccine for it. At least that's the goal. And they're getting closer and closer to that. In the midst of all this COVID-19, I did hear Fauci talk about, director of NIH, that we are getting closer and closer to a universal flu vaccine. So hopefully that'll come too. So that flu doesn't get us the next time this happens. Okay, so somebody asked a question about the resistant, or how the immune system, how could we possibly be infected twice with the same virus? The potential, that the reason we think that maybe you can be reinfected again is that, so in the immune system reaction, when we have immune reaction to a virus, a bacteria, part of that reaction is that our immune system should have something called memory. Meaning we save some of the immune cells in case we ever see that same strain, that same virus again. Now, in theory, those immune cells, those memory cells, should stay around for a while. Sometimes not forever, hence why we have to get booster shots for some things. But it seems for this particular viruses and other coronaviruses, something is going wrong with memory. Probably something directed by the virus. So somehow they're screwing with our immune system's memory so that the immune system is forgetting a little bit more quickly than it should be, which is a little alarming. But it's not completely forgetting, because the second time, the symptoms are definitely not as severe as they were the first time. So usually your immune system's pretty good. You're not going to fool me twice, but for some reason with this virus, the immune system is not bouncing back as quickly as it should be. Okay, any other questions, chats, or anything before I talk about the couple of assignments that we are going to have this week and next? Okay, if I see one pop up, I'll go ahead and stop. Let me jump onto Moodle real quick. And give me my pointer. All right, let me see if I can share this. Share. Everybody should see what Moodle looks like. Okay. And right now they're hidden. I'm going to unhide them right now. Okay. Let me get you guys back up here. Okay. So this is the first assignment that I posted up there. This one is going to be due on Sunday. So it's for those of you who haven't done any of online assignments before, this one is called a journaling assignment, which just means that you can write directly into the assignment. You can just type the answers to the questions directly in there. They go directly to me. Nobody else sees them. So that's the journaling assignment. So if you read the journaling assignment, you're going to watch this video called flattening. Well, it's called What Does This Chart Actually Mean? So you'll watch that video. It's really pretty short. It's about 7 minutes. And they're talking about this idea of flattening the curve, which I'm sure a lot of you have heard about. That's the reason we're all stuck inside, trying to flatten the curve. So watch that video, and then you're going to answer these 5 questions within that journal. So it'll say, start or edit my journal. You'll go ahead and click there, and you can go ahead and start typing out your journal. I'm not expecting this to be like 10 pages long, really just a couple of sentences to answer every question is perfect. That's all I need for that. And you can go ahead and submit it on there. So that is the flatten the curve assignment. And then the second one is not due until a week from Sunday, but it really won't take you that long. You can probably do it at the same time. And this is also a video. This is an interview. The Journal for the American Medical Association, the editor-in-chief of that journal, has a weekly show, I guess you call it, where he talks about different things that are, in the medical field at that time. Clearly, this is an important one. So he has an interview with Dr. Anthony Fauci, who's the director of the National Institutes of Health. You've probably seen his face if you've watched any of the news on this, talking about this specific virus. It's about 30 minutes long, so that, maybe a little bit longer than that. I can't remember. It's about 30 minutes long. And this has a set of questions for you to answer about the video. They're just quiz questions. Some of them are multiple choice, some are short answer. Again, I don't want like 5 pages, a couple sentences. That's all I really need. What I would do is open them up next to each other. So as you're watching the video, you can start answering the questions. They should be in order of how the video is going. So you could watch the video, check out the question, stop it when you get the answer, go ahead and fill it out. But once you start the quiz, so once you open it, you have an hour and a half to finish it. So make sure that you have at least, that half an hour to watch the video while you're answering the question. So make sure you at least have a good chunk of time. And you have to actually hit submit when you're done with the quiz. So you can like skip questions and they're all on the same page. But if you want to just save it through while you're doing it to make sure you don't lose anything, you can go back and edit it before you actually hit the submit button and it gets sent to me. Okay. So my toolbars go away. Where's my toolbar? No, you're not going to give it to me? Okay. Oh, here we go. Maybe? Okay. You're not going to give me all of my toolbars. Manage participants. Okay, there you guys are. All right. Does anybody have any questions? All right, you're welcome to send me an email if you have any questions about either one of those assignments. I plan again on Tuesday to do the same thing. I do have one of my lectures, I can't remember what, I think it's chapter 16, already recorded because I was planning to be at a conference. So I'm going to post that one. That one will not be live, but I'll plan on doing a live one on Tuesday. And then that chapter 16 will be just available for you guys to watch. Okay. Again, if you guys have any questions, please send me an email. I should be on email most of the time, so I should be able to answer you fairly quickly. Okie dokie. All right, you guys, stay safe. Have a great afternoon. Enjoy staying inside. I will see you on Tuesday. Bye.
Bye.